Yeah, I wanted to test, and that seems to be working. Thanks.
Randy is the fastest pistol in town. He pulled like sub-second when you said that.
I think we, hi Jeff. I think we have actually have a packed agenda today. Do you want to get started? Jeff, can you hear me? I haven't heard you speaking.
Like Jeff's trying to figure out his screen.
You should be able to hear me now.
Yes.
Okay. Can you see the slides, or at least the screen?
Yes.
Okay, so we can start.
Okay. Do you want to run it?
Yeah. Harry, good morning, good afternoon, wherever you are. Welcome to virtual 108. Not well, you're at IETF meeting. Any contribution you make to IETF, it's according to IETF rule. Please read not well. No, you're right. Agenda for today, we're going to talk about working group status, and then we have base presentation, Bruno's open source update, we've got Yank update, and multicast update. Working group status. The version 12 has been submitted to ISG. We are still pending AD review. Alvaro, please. Applicability statement draft getting really ready for last call. Probably some wording could be worded better. Yank is ongoing work, thank you. Multicast work just restarted, and we still have PGP and segment routing work. Jeffrey, any comments, any additions before we move?
No. I just want to point out we moved the YAM presentation to before the multicast presentation discussion because we may run out of time, and I want to make sure the YAM gets updated first.
So we start with multicast.
No, we end with multicast.
Okay, cool. Let's see. So we start with Tony. Tony?
You guys don't know how to operate the queue. I put my head in the queue. So first observation, do you guys have a Jabber scribe?
Yes, so, yes.
All right.
So I'll be doing the slides. Jeffrey is going towards the Jabber.
Oh, good point. Actually, I tried the Jabber link. It doesn't work for me. So can someone be the Jabber subscriber?
Jeffrey, the Jabber is synced into chat window in Meeteca.
Chat window.
So on your left, you can go into chat. This is where you see Jabber.
Actually, I couldn't see this. Oh, yeah, I see it. Yeah, thank you. Yeah.
Cool. Okay. So base spec update IETF108 update from 12 to 12. Next one, please. I'll talk about one more thing I think is interesting we could start working on, and one observation minor on the spec. Okay, next one. So stunningly, from 12 to 12, nothing happened. We have all the review. The spec is sitting there waiting for ISG reviews and so on. All the comments are closed. All the people readability. There was a lot of readability improvement that have been done. All the stuff is incorporated. Next one, please. So what was happening is cool new stuff. Well, Bruno did tons of cool new stuff. He'll talk about the stuff. From my side, there are two things. So one thing is we should be probably starting on some draft, which is the optional horizontal link forwarding. There's a bunch of interesting use cases. I don't think it should be part of the base spec, but something that people can implement optionally. Even if they implement it optionally, it will work fine with base spec that does not support it. The second one is a minor gripe I got. Well, it's not really a gripe. Python 2 to Python 3 migration has been one of the worst things that happened in tech recently. So when you compile the model on Python 3, it looks that Python went from set to frozen set and from hash to frozen hash set. And that actually breaks people code that wrote for Python 2 and work fine, because the model generated code implies that those things are hashable, but they're not. The fix is to annotate the model to tell Python that those things are hashable. I did not choose to change the spec. I think this is very circumstantial and particular to a programming language. Anybody interested in this in the schema that is actually annotated for Python? So those are comments in the special. Thrift supports that out the box. Anybody interested in a schema annotated for Python 3? Please just contact me and I'll forward you the stuff. But I think it would be detrimental to publish that in the main spec. That's it. I'm done.
This is Bruno. One comment on that last point. My code is implemented in Python 3, and I did not need to annotate the model. I solved it some other way, so you can look at my source code if you want to see how that's done.
Okay, so that's probably another interesting discussion on the list if somebody's hacking Python. I talked with someone and they wrote some code and I looked at it. They was trying to modify actually the schema objects and it wouldn't work because of the hashable problem. Cool, so that's it. I'm done.
Thank you, Tani. So Bruno is next, right? Jeffrey?
Yes.
So who is running the video and what do we do with it?
I'll be running the video. Just give me permission to share it.
You are a chair. So let me stop sharing.
How do we give you permission to?
You don't need the permission. You're the chair. You have the permission. On your left, you have icon of.
Well, Bruno, I got the message on my screen saying that Bruno is asking to send.
Yeah. Can you hear me?
Yeah.
Yes.
Okay. And can you see this?
Yes.
Okay. I'll see if this works. I'll play it.
My name is Bruno Reisman, and I'd like to give an update on Rift Python, which is the open source implementation of Rift. Since the IETF 105, which is when I gave my most recent presentation, we've added the following features to Rift Python. Number one, negative disaggregation, which is needed to deal with certain failure scenarios in multi-plane topologies. That feature was actually implemented by Mariano and Tommaso from Roma University. Two, fabric bandwidth balancing, which spreads the traffic evenly across multiple parallel links according to the available bandwidth. And three, performance monitoring, which helps us discover bottlenecks in the code. Let's dive right in and start with multi-plane topologies. Up until now, Rift Python only supported single-plane topologies, such as the one shown in this diagram. In a single-plane topology, every superspine node is connected to every spine node. As a result of this, the superspine nodes quickly run out of ports. To deal with the limited number of ports on the superspine nodes, we introduced the concept of multiple planes, such as the blue plane, the red plane, and the green plane in this example. The superspine nodes in each plane are connected to a corresponding subset of spine nodes in each pod. In order to make negative disaggregation work, we also need so-called east-west interplane loops that interconnect the superspine nodes in the different planes to each other. These east-west top-of-fabric links are only used to carry control plane traffic and not user plane traffic, and for that reason, they can be low-speed links. Rift Python includes a configuration generation tool that takes a very high-level description of the topology, the so-called meta topology, as input, and generates detailed configurations for individual Rift nodes as output. This tool has been enhanced with the ability to support multiple planes. Here we see an example of a multi-plane topology generated by the configuration tool. In this example, we have 3 pods, and we have 3 planes, and we have east-west interplane loops to connect the planes to each other. In these multi-plane topologies, there are new failure scenarios that can be fixed with negative disaggregation. Before I get into the details of negative disaggregation, let me first say a few words about disaggregation and Rift in general. One of the defining features of Rift is that it uses a default route for northbound traffic. That default route works fine as long as there are no failures anywhere in the topology. But if there is a failure in the topology, it's no longer possible to use a default route for all northbound traffic, and it becomes necessary to install more specific routes for certain prefixes to route the traffic around the failures in the network. This is exactly what disaggregation in Rift is. It's the installation of more specific routes to route the traffic around failures in the network, and to do that in a fully automated way. There's actually 2 types of disaggregation in Rift. One is called positive disaggregation, and this type of disaggregation deals with most types of failures in the network. Positive disaggregation was already implemented in Rift Python some time ago, and I described it in detail in my presentation at the IETF 105. What I'm going to talk about today is the other type of disaggregation, which is called negative disaggregation. It works in addition to positive disaggregation to deal with one specific type of failure that only happens in multiplane topologies. Even though you don't need negative disaggregation in single plane topologies, it is still one of the most interesting and most novel parts of Rift. And I hope and I expect that I will have an influence on the design of other routing protocols as well. In order to understand the concept of negative disaggregation in Rift, you first need to understand the concept of negative prefix advertisements. All routing protocols up until now have used what Rift would call a positive prefix advertisement. When a routing protocol advertises a prefix, it is saying, I know how to reach that prefix. If you have any traffic to send to that particular prefix, you can send it to me and I will get it to its final destination. So in other words, a positive prefix advertisement is used to attract traffic for a certain prefix. If there are multiple routers advertising the same prefix, then the rule is that the most specific advertisement, the one with the longest prefix match, wins. This concept of using the longest prefix match is supported in current generation hardware. Rift introduces a new concept, namely the concept of a negative prefix advertisement. When a Rift router negatively advertises a prefix, what it's saying is, I don't know how to get to that prefix. If you have any traffic to send to that particular prefix, you better not give it to me. In other words, a negative prefix advertisement is used to repel traffic for that particular prefix. A router that receives one of these negative prefix advertisements is supposed to use any other available route to get the traffic to its destination, even if that other alternative route is less specific. One thing to keep in mind is that a negative prefix advertisement is a control plane concept only. Just before Rift installs these routes in the forwarding plane, it translates negative next hops into positive next hops, and we'll see the details of how that actually works in one of the later slides. This slide shows the type of failure that negative disaggregation was designed to fix. In this slide, we have a topology with 3 pods and 3 planes. Pod 1 is completely disconnected from plane 1 because both of the links that connect pod 1 to plane 1 have failed. Pod 1 is still connected to plane 2 and plane 3, but it's disconnected from plane 1. Similarly, plane 2 is still connected to all 3 pods, and plane 3 is still connected to all 3 pods. But as we mentioned already twice before, plane 1 is disconnected from pod 1. Positive disaggregation cannot fix this particular type of failure. In positive disaggregation, a node starts advertising a positive disaggregation prefix when it notices that it can reach a prefix that one of its neighbors in the same plane cannot reach. In this particular scenario, that doesn't happen. In plane 1, none of the superspine nodes can reach pod 1, so nobody initiates positive disaggregation. On the other hand, in plane 2 and plane 3, everyone can reach pod 1, so once again, no one initiates positive disaggregation. The first step in negative disaggregation is for plane 1 to discover that it's disconnected from pod 1. In order to achieve that, these top-of-fabric nodes run 2 instances of the shortest path first algorithm. The first instance, or the first run, which is considered the normal run, is used to populate the forwarding tables. In this normal run, the east-west links between the planes are not allowed to be used, and as a result, the superspine nodes in plane 1 will not discover pod 1 and will not install any routes to the leaves or the spines in pod 1 in the forwarding table. If negative disaggregation is used, then the top-of-fabric nodes will also run a second run of the shortest path first algorithm, which is considered the special run. In this special run, the east-west links are allowed to be used. And as a result, plane 1 will discover routes to pod 1, namely routes that go through one of the other planes. These routes to pod 1 are not actually installed in the forwarding plane, but they are used to trigger negative disaggregation. Once the superspine nodes in plane 1 have discovered that they're no longer able to reach pod 1, they will trigger negative disaggregation. They will start advertising negative prefix advertisements, which are indicated by these red arrows, to tell the network that they're no longer able to reach pod 1. They're telling the rest of the network, if you have any traffic to send for any prefix in pod 1, don't send it to me because I have discovered that I'm no longer able to reach pod 1. The show disaggregation command in Rift Python allows you to see the negative disaggregation prefix that a node originates. In this example, you can see that super12 originates negative disaggregation prefixes for each of the prefixes in pod 1. Unlike positive disaggregation, negative disaggregation is transitive in the following sense. When the spine nodes receive a negative disaggregate prefix from each of their parent nodes, they realize that they themselves are also no longer able to reach pod 1. In that circumstance, they propagate the negative disaggregate prefixes to their children, as indicated by these red arrows. Once again, you can use the show disaggregation command in Rift Python to see both the received and the propagated negative disaggregation prefixes on the spine nodes. When the leaf nodes receive these negative disaggregate prefix advertisements, they use them to install special routes in their routing table with negative next hops. In this particular example, when we look at leaf 22, we see a default route that uses all 3 planes to forward the traffic, but then we have specific routes for the destinations in pod 1 that have negative next hops, avoiding sending the traffic through plane 1. You can actually see these negative next hops when you issue the show routes command in Rift Python to look at the routes in the routing table, which is also known as the routing information base, or RIB. Earlier, I mentioned that these negative next hops are a control plane concept only, which doesn't actually exist in the forwarding plane. So just before Rift installs the routes into the forwarding table, it needs to translate the negative next hops into positive next hops. How that happens is explained in this diagram here. Rift looks for the most specific covering aggregate of the negative prefix. Typically, as in this example, it will find the default route. That covering aggregate represents the best path available to the negative prefix. We take the positive next hops of that aggregate and subtract from it the negative next hop of the negative prefix. So we end up with a subset of the next hops of the covering aggregate. Those next hops are installed into the forwarding table, as is shown in the green part of the diagram here. In this diagram, we see the resulting routing table and forwarding table for our example topology. We're looking at the specific prefixes for the leaves in pod 1. In the routing table, or the RIB, we have negative next hops, which indicate that we should avoid sending the traffic through plane 1. In the forwarding table, or the FIB, those negative next hops have been translated into positive next hops, attracting to the traffic to planes 2 and plane 3, which has the net effect of avoiding plane 1. You can use the show forwarding command in Rift Python to look at the forwarding table. For more information on negative disaggregation in Rift, see the blog post or the detailed documentation referenced on this page. The second major enhancement that was introduced to Rift Python since IETF 105 is support for parallel links. Some new keywords have been added to the meta topology file that allows the config generator to generate parallel links in the topology. In this diagram, you can see an example topology that was generated by the config generator with parallel links. In this specific example, we have 4 parallel links on the leaf spine links, 3 parallel links on the spine to superspine links, and 2 parallel links on the east-west interplane links. When you have parallel links into topology, you want to make sure that the traffic is distributed amongst the available links according to the bandwidth available in each link. We'll go through a couple of scenarios to demonstrate how that works. This is the topology that we will be using for our examples. We'll be looking at leaf 1-2, which has 2 parallel links to spine 1-1 and 2 parallel links to spine 1-2. We'll see how leaf 1-2 distributes its traffic across these 4 links in various failure scenarios. Once we start introducing parallel links into the topology, we have to make a distinction between the concept of a neighbor versus the concept of an interface versus the concept of an adjacency. To illustrate that difference, we're looking at the output of the show neighbors command on node spine 1-2 in the topology. Here we can see that that particular spine node has 4 neighbors, but 8 interfaces and correspondingly 8 adjacencies. The reason for that is that we have 2 parallel links to each neighbor, so for every neighbor there are 2 corresponding interfaces and adjacencies. To understand how Rift Python does fabric bandwidth balancing, in other words, to understand how Rift Python distributes its northbound traffic over the available links, we can look at the output of the handy show bandwidth balancing command. On this slide, we have the example output looking at from the perspective of node leaf 1-2. We can see that leaf 1-2 has 2 neighbors, namely neighbor spine 1-1 and spine 1-2, which we can see in the diagram here and here. From the perspective of leaf 1-2, neighbor spine 1-1 has an ingress bandwidth of 20 gigabits per second. This corresponds to the amount of bandwidth from leaf 1-1 to spine 1-1. Similarly, from the perspective of leaf 1-2, neighbor spine 1-2 has an ingress bandwidth of 20 gigabits per second as well. From the perspective of leaf 1-2, neighbor spine 1-1 has an egress bandwidth of 60 gigabits per second. This corresponds to the total amount of bandwidth that leaves spine 1-1 to any neighbor except back to leaf 1-2. Similarly, from the perspective of leaf 1-2, neighbor spine 1-2 also has an egress bandwidth of 60 gigabits per second. Rift Python distributes the traffic amongst the neighbors in a way that is proportional to the product of the ingress bandwidth and the egress bandwidth of each neighbor. So in this particular example, node leaf11 will end up sending half of the traffic, 50%, to node spine11, and the other half to neighbor spine12. In this example, there are actually multiple parallel interfaces to each neighbor. In that case, the traffic is distributed across the interfaces within a neighbor group according to the bandwidth of each individual link. So in this particular example, each interface ends up with 25% of the traffic. The rules that I have described so far for distributing traffic over the interfaces are actually slightly different from the rules that are described in the RIFT specification. But that's okay, because the RIFT specification explicitly allows implementation to pick their own rules subject to specific conditions. If we look at the output of the show forwarding command, we can see that the northbound default route actually turns out to be an ECMP route. It distributes all the traffic equally across all 4 available links. RIFT Python uses percentages as the next hop weights to make the output easier to read. Now let's look at the first failure scenario. In this failure scenario, one of the links between leaf12 and spine11 has failed. Leaf12 still has 2 neighbors, namely spine11 and spine12. The ingress bandwidth from the perspective of leaf12 into spine11 has been reduced from 20 gigabits to 10 gigabits because of the failed link, whereas the ingress bandwidth into spine12 is still 20 gigabits per second. The egress bandwidth has not changed for either of the spine nodes. As a result of this, spine11 gets 33% of the traffic, 1/3 of the traffic, and spine12 gets the other 2/3 of the traffic. Within the interfaces, each interface gets 1/3 of the traffic. What we end up is once again an ECMP route, but now the traffic is equally divided amongst the 3 remaining interfaces. Now let's look at a more interesting downstream failure scenario. In this example, spine11 has 2 failed uplinks towards the superspines. In this example, leaf11 still has 2 neighbors, namely spine11 and spine12. Both spine11 and spine12 still have the full 20 gigabits per second of ingress bandwidth. However, spine11 has a reduced egress bandwidth of 40 gigabits because 2 of the uplinks have failed, whereas spine12 still has the full 60 gigabits per second egress bandwidth. As a result of this, leaf12 decides to send only 40% of the traffic to spine11 because it has reduced capability to forward the traffic to the rest of the network, and it decides to send 60% of the traffic to spine12, which still has full capacity to send traffic to the rest of the network. Within the link groups of each neighbor, the traffic is distributed equally amongst the links because each link has the same capacity. What we end up with is a non-equal cost multipath route where 20% of the traffic is sent over the links to spine11 and 30% of the traffic is sent over the links to spine12. The last new feature that I'd like to talk about is performance monitoring, which allows you to find out where RIFT Python spends its time in its code. What really helps here is that RIFT has been specified using formal finite state machines, or FSMs. Most interesting activity in RIFT occurs as the result of events being dispatched to finite state machines. We enhanced RIFT Python to allow you to keep track of exactly how much time events spent waiting in the queue, waiting to be dispatched to the finite state machine, and once they were dispatched, how long it took to actually process that event. RIFT Python also keeps track of various unusual processing times so that you can quickly see if there is a problem. That concludes my update on RIFT Python. I'd be happy to take any questions.
Right on time.
Perfect, yes.
Hello, can you hear me?
Yeah, go ahead.
Yeah. Hi, I'm Anurag from Siena. I just have a couple of questions. What is the difference between a route withdrawal and negative when you mentioned the negative prefix advertisement?
Yeah, so a route withdrawal, if you first positively advertise a prefix, you're saying, I can reach this prefix, it's okay to give traffic to me. If you then withdraw that prefix, you're saying, I can no longer give that prefix, but I'm not making any statement about whether or not you should send it somewhere else. If you negatively advertise a prefix, you're explicitly saying, don't give it to me. If you have some other route to send to it, then use that prefix instead. And so what, that sounds the same, huh?
Yeah, I mean, what my assumption was withdrawal or deletion will get it out of your ribbon entry, like in a normal RIB terms. I'm not an expert in RIF, but it seems like the term used here seems similar to me, but it's achieving the same purpose at the end of the day. And that, I mean, maybe there are certain little details which I don't understand, but that was primarily what my confusion was. The second one, maybe we can discuss offline as well. The second one was when we are talking about balancing in terms of I wouldn't say balancing, like when you mentioned that, I think you mentioned plane 1 was completely disconnected from pod 1, right? That was an example in there.
Yeah.
So we did have red, blue, and green planes. So effectively, every pod also has red, blue, and green. So in an ideal scenario, unless you take down all the 3 planes, it should never be disconnected. Is that true to understand?
That's correct. The pod as a whole will still be connected to blue and green. But if
Okay.
you look at the spine switches,
Right.
they are actually connected to a specific plane. So
Understood.
from a leaf point of view, you cannot just have a default route that points to all 3 spine routers, because if you accidentally give it to the red spine, you've already gone into the red plane, but that spine may be disconnected from the super spines, and so then you're in a black hole. Okay, for that reason, you need to already at the leaves remove the possibility of sending it to the red spine router, and that's why you need this.
And-
can I answer the first question? So the question was, what's the difference between a withdrawal and negative? And the key point, I guess your video really says it, is that the negative is actually always a reference to the aggregation above it. And so when you send something negative, you say, oh, the aggregation above minus this, right? So that tells the receiver of the negative to basically install the positive for the rest of the aggregation above. So negative by itself doesn't mean anything. It's always as a reference to the aggregation above it.
Yeah, I mean, but effectively
helps.
it's doing the
Yes,
same thing.
we've got time for one more question. We'll have to continue in 2 minutes.
Can I ask?
Okay, I'll let Kyo speak. So Bruno, thanks for breaking the spec. And I think it didn't come out why you can simply implement a different algorithm for the bandwidth, because Rift is loop free. So you can send it out any viable link pretty much. And it will get there without a loop. Yeah.
Super. Thanks, Tony. Bruno, good morning from California. A quick question. As I understand, once you get the negative route, you would, if there is an exact match route or a covering prefix, you would actually take that next stop out. How many levels would you go up, or would you just stop at the first covering prefix? And if you stop at the first covering prefix, say that prefix disappears because you get withdrawals on all the routes, would you still go a layer up and keep on recursing it till the negative prefix is received and preserved?
So let me give a concrete example, right? In my example, I sent a negative advertisement for a prefix in leaf in pod 1. right? So if somebody tries to send a traffic to that particular leaf in pod 1, it will hit the negative prefix. And in the forwarding plane, the negative next hop will have been translated into positive next hops that say only use planes 2 and 3. Now, if you send the traffic to any other pod, for example, to a leaf in pod 2, there will not be a specific route. It will just hit the default route, and it will use all three spines, all three planes to get there. So I hope that answers your question.
The short answer was yes, by the way.
Yeah, so basically the big difference between the negative and positive is not transitive. It will only go one level down. Whereas the negative, if all the switches connected to a plane tell you I'm negative, then you have to propagate it farther down. And that's the only solution that works, because in most extreme cases, you have to decide right on the server, if it's multi-home, whether you go, which plane you go. Because if you started the server towards the wrong plane, you're already stuck. You basically have to go through the bottom of the fabric to another plane again and basically make a huge loop 4 times through the fabric. That's all not that intuitive unless you read the spec very carefully.
No, Tony, that was not my question. My question was,
okay, then I'm sorry.
When you take the covering, when you take that next hop for a negative prefix out from covering prefixes, if that covering prefix disappears, then would you go a level above?
Correct. Yes, you have to.
That's the short answer. Yes.
Yes.
Thank you.
There is a very explicit example in the spec where it shows you that you have to go to the first positive covering prefix to actually know where you can forward, and then chop out the negatives. Yes.
Thank you.
Guys, we'll have to cut you. Sorry. Please continue on the list. Great discussion. So next one is Young, right?
Yeah, Sandy.
Sandy, are you there? Cannot hear you.
Yeah, she's just in.
Can you hear me?
Yes.
Oh, okay. Thank you. Hello, everyone. And this presentation is for the update of Rift Young. We have co-authors Yuehua, Shaowen, and Xu Feng. Next page, please. My screen burnt. Page down. Is something wrong?
Do you see slides moving?
No.
Huh.
No.
Let's try again.
Okay. Let me continue. This data model is defined according to the Rift protocol structure. This model includes protocol configuration, state information, and some notifications. Some features are added to enhance the protocol. Thanks Bruno, Tony for their detailed review and comments. Next, please. So let's see the update of this version. The major changes include editorial modification and the model update. The editorial modification is according to RFC 84007. The update of Young model is according to the implementation experience. The 01 version is not the final version. It will be updated again in a few days. Next, please. This is the configuration part. Multiple Rift instances are supported. The keys of the nodes include name, system ID, level, and so on. Variables that can be configured include port, level, flood reduction, link capabilities, timers, and security items, and so on. For flexible management, different multicast address or part can be used for different instances. Next, please. So this is the state part. All the read-write nodes are also be the state part. Except then, there are some read-only parts, such as
Looks like we lost Sandy. Can you hear me? Hello? Can anyone hear me?
Yes, I can hear you.
We can hear you.
Okay. So we may have lost Sandy. She did mention earlier that she had some trouble during the beer session as well.
So we can probably summarize on behalf of Sandy. So there's some additional work that needs to be done. The base model is in pretty good shape. It's aligned with 8447. So we'll be looking forward to updated version. But I think, again, we are very close to be done on the young side of things. And I think we can move now to, so the continuation of presentation is really description of changes. I don't think it's worth going through. Authors of Rift, please review the young model, make sure that it conforms to what you want to see in terms of configuration, operational states, and so forth. Let's move to multicast.
Okay, so before I start talking about multicast, I want to point out that since that this session will end exactly at in 8 minutes, so we'll probably just continue to that endpoint, and then everyone will get disconnected without saying goodbye. So
Jeffrey, it looks like they stopped cutting. At least they didn't cut routing on Monday, so maybe.
Yeah, they did that.
Like 5 minutes credit or something.
Yeah, they've cut 5 minutes before the hour now. Yeah.
Right. Okay. So I will start talking about the Rift multicast very briefly, and then hand it over to Pascal. Next slide, please. So previously, we have talked about that we borrow the PIM bidirectional pure PIM concept, establish bidirectional trees, whether it's star G or star G prefix or star G, and basically every router, starting from the routers with who wants to be on the tree, so they hash to a north neighbor and then sends equivalent of PIM joins towards the north neighbor. And those joins will stop at some subtop nodes, forming subtrees. Then the next problem is, how do we join those subtrees together or by a virtual rendezvous point link? The idea is that we form a spanning tree among those relevant subtop nodes and top nodes. We rushed out a 0-1 revision with just a bit more details, including the idea of per neighbor flooding scope, so that we can target the joins, and I added some strict schema, and then finally I try to provide some details on the building the spanning tree. The previous version had the idea, but I wanted to add some details. It turns out that we may have found some holes in that that cannot handle all the situations, and so Pascal is thinking about the different way to do that, and that's what he's going to talk about in the remaining time. And we may so I'll just hand over to Pascal now, skipping the some slides. Please look into that idea of per neighbor flooding scope That is something new that we are introducing for multicast purpose. It's subject to discussion. Pascal, you can take over now.
Jeffrey, which slide do you want to skip?
Just skip to the pictures.
Yeah,
Continue.
yes, please.
Yeah.
So,
and he has animations. Is this a PDF or?
This PDF.
Okay, I will skip the animation, no worries. So what you have here is basically a tree being built from the leaf level up. So you see that each leaf selects a parrot. So it can be done in any fashion. And you go up like this all the way to the subtoph. And as you build this, you're building a collection of trees. So you see the orange tree, which is rooted at N1, and the green tree, which is rooted at N2, and the purple tree, which is rooted at N4. And some of those trees, they are rich leaves, and some of them, maybe M3 never got a child, but it's an option to, if you want to distribute traffic only to leaves, you don't have to build this green tree. But if you want to distribute traffic to every node, including the nodes inside the network, then you need to also to build this green tree. As you've done that, you realize that you have actually built a collection of trees, but you have not built a single tree. So what you want to do now is interconnect all those subtoph using the toph plus subtoph level. And basically, as Jeffrey said, we build a virtual RPL, rendezvous point link, between the toph and the subtoph. The question at hand is, how do we build this tree? So next slide, please. So you see what you want to do is interconnect the roots here and make a single tree out of all those 3 trees. One slide up. Okay, so this is where we build the spanning tree as I discussed. Next slide. Okay, so building the spanning tree can be easy. For instance, if we have a complete bipartite mesh, meaning that every subtoph is connected to every toph, then basically you can elect any toph node, call it a root, and you've got your tree. But if there is any breakage, that may not hold true anymore. So if it's not fully connected, then we need some protocol to build the spanning tree that we are after. We'll note that overall, the toph plus subtoph cannot be fully partitioned. There cannot be the left and the right of it. This seems to happen when you have the multiplane fabric, as we saw for the disaggregation earlier. But that's when we need this ring to interconnect them. Because if there was a full partition of toph plus subtoph, the left piece, the right piece, then you could not disaggregate at all because you would not be able to know what's going on the other side. So we take the assumption that the toph plus subtoph cannot be partitioned. It's not partitioned. And if it's not partitioned, then we can effectively build this tree. Next slide. So the idea at hand, and you'll see that will progress. So don't ask yourself too many questions. How do you do hashes? How you distribute multiple trees, etc. For now, we're just building a single tree, and we are looking at how we do that. So there are 2 things you need to do. You need to elect a root, and you need to find maybe the shortest path tree to that root. So the simplest idea is to say, hey, let's pick the node between the toph and the subtoph that has the least system ID, or the highest or the smallest system ID. And you'll see why I picked the lowest, but initially we started with the highest. And then use the up count as a distance toward that root to build a tree. So the simple idea, if you like, is to consider this as a distance vector prime. And the distance itself would be a composite of the system ID for the most significant bits, and then the hop count to that system ID. So we would, for instance, advertise that composite distance in the node TIEs, so that's reflected. So what you do is you look at all your neighbors, and if one of them advertises a metric which is lower than the one you already know, so you start with your own system ID hop count 0. So if one of your neighbors sees a system ID that is lower than yours, Then he will advertise that, you will pick it, and you say, oh, it's better than mine, so it's a lower distance. Let me pick his system ID and increase the hop count and advertise that. And as you do that, you have a simple distance vector which builds the animated tree. But I actually split this animation in the next slide, just in case. The next slide, please. So what you see here is the same thing as the animation we were missing. So you see that the lowest system ID is S1. So very soon N3 and N5 see that the lowest distance for which the system ID is the most significant bit is S1 hop count 0 as advertised by S1. So N3 and N5 will start advertising S1 hop count equal 1, which causes for the next phase, bottom left, S3, S4, S5 to pick N3 as their parent. And so now S3, S4, S5 advertise S1, 2. And N4, which was actually disconnected from S1 from the start, will now pick one of the parents. And we need to just, at this point, you could select anyone, but we'll discuss how we do all this. So you see, by just doing this simple distance vector, which routes at the lowest system ID, using this composite metric, we already build a spanning tree. We build one. So that's a very easy spanning tree to build. It has a number of drawbacks. The major drawback of this method is that if you look at it, if you are really very well meshed, then S1 will probably get most of the work sending the packets out. It's not really exemplified here. But the root of the tree will, for instance, if it's a tough node, it will see all the sub-tough nodes. Inside the tree, there will be basically a hub and spoke topology. And the hub will have to make all the copies. So it will have a lot of burden making many, many copies. Next slide, please. Okay, so to look at this problem, we could say, hey, there's one way to kind of split the work of doing all the copies between the tough and the sub-tough. And one kind of cool way of doing this is to say, hey, why don't we have a sub-tough node act as the root? So what would happen is you would split the tough in a number of groups, which has basically each of those groups would have a size of the square root of the total number of sub-tough nodes, which basically makes it so that this N1 would see only, okay, the parents that the sub-tough would pick, the other sub-tough nodes would pick, would be in one of those groups, everyone in the same group. So the tough nodes that would be used in the tree would be just a cardinal, which would be roughly the square root of the number of sub-tough nodes. And that's the nodes that N1 will see going up, which means that N1 will make square root of cardinal of sub-tough copies, and each of the member of this group will make the same number of copies. So you basically end up with the cardinal of sub-tough number of copies total. But you have spread the number between N1, which does the square root number of copies, and then square root tough nodes, which do each one of them square root, which gives you the total. So that's kind of a way to say, hey, let's split the replication game between the sub-tough and the tough. And so you see that by doing this, you already kind of share the load, but you still build a single tree. Next slide, please. So this single tree looks like fine for distributing mice flow, for instance, but you see that it's all using the same length all the way through. So first thing you would say, hey, okay, I can use one single tree or shared trees for all the mice flows, which end up distributing to all the leaves. But I would like to make multiple of those trees so as to distribute the flows over different sets of lengths. And that means electing a different group and different groups of tough for each of those number of trees. That's the easy part. The hard part is when you have a mice flow, how do you allocate to which tree that thing goes? because you cannot stamp anything in the packet. So that's the hard piece. And I see that Tony is on the queue. Tony, do you want to ask a question? No, Tony withdrew himself. No.
Chair's asleep, so I just grabbed the mic. All right, all brilliant. That implies that the hash function has to be uniform across all the nodes, right?
Exactly, that's what the problem is. That's why I'm saying it's very hard.
Right, and the problem with that is, of course, that you have to agree whether you hash into 8-bit or 16 bits or 32-bit. So you basically nail to the number of the trees you can use.
And you want to make sure that everybody has the same information, because if you basically say, I've built trees 1, 2, 3, 4, and one node for some reason doesn't see tree 4, and tree 4 is the tree selected by all the other members, but not by him, packets are going to loop. So
right, yeah. So that's
very hard.
It's a limitation. Yes, it's a limitation. Otherwise, brilliant. Yeah, thanks.
Yeah, so I'm not saying we need to do the hash. I would be a lot more satisfied if we could tag the packet. When you inject the packet in a multicast, you could tag it with the tree ID or something to say, hey, I'm using this tree. So the source randomly selects which trees, and then we flood that tree.
We can play a trick with relying on flow ID in V6 or, something like this. But at the end, I think the problem that you're still facing is how many trees do you build, because that has to be uniform, right? You don't have per group state, but you have to agree how many trees do you have. And that's a limitation I see.
You have to agree. Everybody has to build the same trees. And everybody must agree that something called Tony is that particular tree, and somebody does not mix, the names. And so that's...
We actually don't need to worry about loops because you will only accept traffic from one of the specified North interface. So you will not get into loops. Even somehow different trees are picked by different nodes for short in transition states. But we can talk about that offline.
Well, inside the RPL, you may create loops. Outside the RPL, traffic that starts going down still goes down. Traffic that went up has to go up. So it cannot loop. But inside the RPL itself, if the trees are kind of mixed up, you can get anything. So that's why I'm concerned. I mean, I agree that...
RPL, okay. Got you.
Yeah. So there is this. But we see that there could be a way that we have not designed yet, where we make sure that if we build 10 trees, everybody understands that the 10 trees are the same tree. So they have numbers 1 to 10. And then basically, by the idea of the flow, by looking so many bits on the multicast address, we could just assign the tree. But the hard piece is to make sure that everybody understands which tree is which and how it's named. So that was just for the mice flow. We said for the mice flow, we just pre-built one tree or one collection of tree, and the mice flows go to every leaf, regardless of whether the leaf requested this flow or did not request this flow. For the giraffe, and you'd have Jeffrey to redefine giraffe because I forgot. I thought it very nice, but I forgot what you meant by this. And elephant flow, which means very, very fat flows going to very few nodes. Then it makes sense to build a dedicated tree for this thing. And there are two cases, the case where you're looking for a prefix, so it's longest match, or the case where you're using, you want to build it for a particular group, in which case it's exact match. Now, I'm also concerned, make sure that when we do this prefix game, so having longest match, we never want to have a mice flow that would be spread over the other trees. So I'm still a bit concerned with the G prefix. I mean, there must be a rule somewhere which ensures that whatever subnet of this prefix, whatever multicast address built out of this prefix we use in the future, in anywhere, it's always to be routed within this tree, because this tree does not distribute to everyone. It only distributes to people who register to the aggregating prefix. So the longest match, Asmi can discuss that on the list or when we have more time, but the longest match game for me is hard to play when we want to use default for mice. Okay, so we'll discuss that. So after that, we end up with the same game. We want to probably select a different route in the RPL. So that means probably hashing all the root, the system IDs with the group G that we are talking about, and picking the least hash. But then again, we want to make sure that everybody sees everybody. Otherwise, the least hash may not be the same for everybody. So it's already, each time we use a hash in this discussion, we have kind of a problem of making sure everybody has the same information about everything. And then, like I said earlier, if we want to use the square root of square root to divide the work of replicating, then we need to select a different group of nodes of cardinality square root blah for each of those groups G, which means maybe another hash or something. So again, we have this problem of hashing, making sure that everybody sees all the groups, so the hash always resolves to the same for everybody. And so you see hash of root G and root right after it, root system ID, that's what's meant. The reason why I did that is the hash make collision. If you want to make sure that you pick the least hash, but then you avoid collision, you have to put the hash of the system ID of the root with G, and then you have to put the non-hash system ID, which is unique. So at the end, you get something which is unique. So I played it once for the root, I played it second time for the TOF group ID, and then at the end, the hop count for that particular tree. So that's how you could build it.
Finish up.
I'm done. It's pretty much this. If you go to the next slide, I'm not even sure there is a next slide. Well, okay, there is just an exemplified result of the discussion before for one tree. So you see how this thing gives you a tree that can be used for BDR replication. But you see the bottom line, the real problem that we have now is if we want to use hashes, we want to make sure that everybody sees the same thing. Otherwise, we'll have to distribute names or do something else. But it's very hard at this point to it's very easy to build one tree. It's very hard to build multiple trees and make sure that by reading the packet, everybody understands the same tree. That's what I'm concerned with at this point. And I'm done.
Thanks, Pascal.
Thank you.
So we are after 7, so we need to stop. Thanks everyone for joining us. Very good progress. We'll continue working on segment routing, multicast, and some other pieces. And I really hope to see you in person next IETF. If not, we'll just meet virtually. Take care, everyone.
Thanks, bye.